I don't know if this chapter is right. I don't think it might be right in your book, Brian. I'm not sure. But it should be diode application and troubleshooting. And we got an introduction into um, a rectifier, a halfway rectifier last class. Oh, let me turn on the projector. That would help a little bit, wouldn't it? So no, we're not near the transistors. So what we end up being is this is called a characteristic curve for a diode. So this would be forward bias. So how do we forward bias the diode? So of course we got the symbol, right? So it starts off with this, and I'm gonna stop coloring these things in for after a while. But the actual symbol is supposed to be colored in, and then we have a bar. And what do we call this guy right here? Yeah, we call this the cathode. And what do we call this guy right here? And then we can bias it two different ways. We can forward bias it, and then we can reverse bias. Now, when we forward bias it, it acts like a closed switch, right? But it's not actually, because a closed switch would drop 0 volts. If this is silicon, then it's going to drop approximately what? Yeah, around 0.7 or 700 millivolts. And this is approximately, like I said, some books teach 600 millivolts. Our book teaches 700 millivolts. Which one's right? Both of them. Huh? I said some books teach 600 millivolts for a silicon junction. Some books teach 700 millivolts for a silicon junction. So who's right? You know, it's only 100 millivolts difference, so it didn't really make any difference because it's an approximation anyway. It just gives us an approximate voltage drop. So what happens when we start forward biasing this thing, and how do we forward bias it? Sorta. If I came up here and measured a positive on the cathode and a negative on the anode, I'd throw my diode away. It's usually it's in respect to. So if this guy right here is this, then this guy's got to be bigger, right? You understand? So it's got to be, so it's in respect to. So the cathode has to be made negative in respect to, right? So over here I could have 5 volts plus 5 volts. Over here I would have 4.3 volts, but they would both be plus. Or I could come over here and have a negative 6 volts, and over here I would have a negative 5.3. It's in respect to, right? So a lot of people says the cathode has to be negative and the anode has to be positive, but you're almost never going to see that. It's in respect to. So the cathode has to be 0.7 of a volt more negative in respect to the anode, or the anode has to be 0.7 of a volt less negative than the cathode. Does that make sense? Very, very important. So if you ever see it on the test where it says the cathode has to be negative and the anode has to be positive, what are you going to mark? False. So is the cathode negative on the top one, is the cathode negative and the anode positive? No, they're both positive. On the bottom one, is the cathode negative and the anode positive? No, they're both negative. So what we got to learn is in respect to, right? You understand? So that would be false. If you saw a true and false that says the cathode has to be negative and the anode has to be positive, you're going to say that's what? False, yeah. So what happens when we start forward biasing this thing, right off the bat, it's not an insulator, it's not an open switch, there's a path through there. So what happens is we have a very slight current flow, and then when we hit around 7/10 of a volt, we hit this knee, and then it comes up. Now it's not vertical; it's a closed switch. That would be vertical, but it's not a closed switch. It's a diode. It's a semiconductor. It's got material. It's got a flow through. So there's a real small R, even when it's forward bias. So that means when the current goes up, so this measurement right here, by the way, we call the VF. We talked about that in class. So the VF varies with current. So the higher the current, this is why 7/10 of a volt is approximation. Because the higher the current, the more it's going to drop. The less the current, the less it's going to drop. Until we get around 7/10 of a volt, and then the thing's going to cut off, right? You understand that? Now over here on the reverse bias side, we have this current right here we refer to as leakage current. But it's very, very small. And then this is a break in the line. And then eventually we're going to get up to this voltage, and we're going to literally push current through the semiconductor in the reverse direction. When that happens, it's a cascade effect, and this will probably damage the diode. So what we're looking for is this books call this the peak inverse voltage. Data sheets usually call it the reverse breakover voltage, and they usually designate VR. Which is bad. So if you ever exceed this, and all this is going to be in something that we call the data sheet for the part number that we're looking at. So the part number, by the way, most silicon diodes start off with a 1, indicating one junction, and then it's come over here and it's got a designator, and this is what and this is pretty standard. So if you ever pick up a part and see a 1N something, then it's a diode, right? If you see a 2N, it's going to be a bipolar transistor, but we'll get to those. So we'd look up the data sheet on the device, and one of the things it's going to give us, first of all, it's going to give us VF, it's going to give us VF, and then it's going to give us a VF max, which would be up here somewhere. And that's when you got it operating at the maximum current. So if you put too much current through it, even in the forward bias direction, and you put too much, it's going to burn it up anyway because it's got an R component, right? You understand? And so when we're dealing with R, then power is equal to I square R, right? By the square. So eventually, if you put too much current through it, it's going to burn it up too. So we got two things that could cause our diode to go bad. We could exceed the breakover voltage, or we could exceed the maximum current flow of the diode, and it would cause it to go bad. And of course, if things that makes sense. So we'll look at those at the data sheet. So this is something on a regular diode we don't want to do. We don't want to do this, right? We don't want to hit this breakover, and then we don't want to get this I forward max. We don't want to exceed that. Either one of those, the diode could be damaged. So when you buy a diode, you just got to buy a diode. And I think I told you the story. We were building power supplies and it kept burning up resistors because all the lab says is get a 100 ohm resistor, but they was running like 15 volts, right? You understand? 100 ohms, 15 volts, right? You understand that? So that's V square, 15 squared over R, 100 ohms, and they were using quarter watt resistors. So what was happening every time they turned their power supply on, it burned the resistor up. And they would come up to me, now I think something's wrong with my power supply. It keeps burning up resistors. But what they didn't do, they didn't say, okay, and what is resistors rated in? What's the three things it's rated in? Not that you're thinking about a conductor. I'm talking about a resistor. No. Ohms. watts, and tolerance. This is what it's rated in. Y'all should have had this in DC. So this is something you got to know. You just can't say, I want a 100 ohm resistor. I want a 100 ohm resistor. Do you want a 100 watt? Do you want a, of course, if I was a salesman, you know, and you came up and say, I want a 100 watt resistor, and you didn't know the wattage, I was going to sell you the most expensive one I got, right? Understand that? So these are the three things that resistors are rated in. Diodes are rated in maximum current, right? And then this breakover voltage. That's the big thing we're looking at right there when I go out and buy a diode. Is how much current can I put through that thing without when it's forward biased when I turn it on, and how much voltage can it block when it's turned off. That's the two main ratings on the diode. In the reverse bias condition, lower left quadrant, the current stays at virtually zero until the breakdown voltage is reached. When the breakdown voltage occurs, there is a large reverse current which can damage the diode. It is not if it's not limited by a relatively large ohm resistor. So what we're going to do is we're going to control this breakover voltage. We'll do this as a team, because what we're going to do, we're going to deliberately break a diode over in the reverse direction. But we're going to have like a 10 mega ohm resistor in series with it. So when it breaks over, we can see the current increase it through the resistor by measuring the voltage drop, right? You understand that? And we'll actually see it break over. I think our diode that we breaks over like around 90 volts. So that's above lethal. So it usually, so we need to know that, right? So this is the breakover region right here. So as long as we keep it below that breakover voltage, then this guy is going to act like an open switch. Is there going to be current flow through it? Yes, there is a path. You have a difference in potential. And what do we call that current that flows through it in the reverse direction? Huh? Leach's current, yeah. So this is a symbol for a diode. We okay? Anode, cathode. How do we forward bias it? Okay. But we can say the cathode has to be negative in respect to the anode, right? You understand that? Or and that's it. Or we can say the anode has to be positive in respect to the cathode. Each one of those would work. So these guys come in all different types of packages. We looked them over. We got most of these. You can get them in a surface mount. You can get them in. I thought I had some of these over here. I think we passed one of these guys around, right? Now, what determines the size is basically how much current they can handle. So it's a lot like a valve, right? Instead, it acts like a check valve. And the valve, the more flow that a water valve has to handle, the bigger it's going to be. And this is also, so the more current this thing has to handle, the bigger they're going to be. So that would be specified by, and how they mount. These are called radial lead devices, because they look like these are called axial lead devices because they look like what? An axle. The ones we're going to be using are these. Well, I'm sorry, we got two we're going to be using. And I think I passed these around. And how can we identify it when we look at the part? So the big ones, like this, what they'll have is they'll have the diode symbol actually drawn on the side. And it's either we can buy the cathode as the stud, or we can buy the or this can be versed around. So that's one of the things you need to know too, right? These guys, though, what we're going to do is we're going to identify these with a stripe on one side, right? So these are the ones we're going to be using, and we're going to use a glass one, by the way, too. It's a small glass one, and it'll have a black stripe. The one that's made in the plastic like this will have a white stripe. So these are a couple right here that we can check. And how do we usually check them to see if they're good or bad? We use our meter on the p-n junction scale, right, or what they call the diode scale. Now, this is the way we're going to calculate these things. We're going to have what we call a first approximation. The easiest way to think of a diode in operation is like a switch. When it's forward biased, it acts like a closed switch. When it's reverse biased, it acts like an open switch. We call this the first approximation, which means it would create a curve like this. So as soon as you forward bias it, it would do this. And then when you reverse bias it, it would do that. And this is called ideal. Normally we use this on high voltages. The rule of thumb is around like 30 volts. What we can do on that is we can ignore this 7/10 of a volt that the things are going to drop. So rule of thumb is 7/10 of a volt or 700 millivolts for a silicon diode. And what for germanium? Anybody remember? 3/10. Yeah. This is by far the most prevalent right here. So all the diodes that we're going to be using is going to be silicon diodes, except in one of our labs. One of the labs that we do, one of the first labs we're going to do is we're going to check a bunch of diodes with an ohm meter, and we're going to determine if it's germanium, we're going to determine if it's silicon, and then if they're good or bad. I think all of these are good. So this is first approximation right here. Well, we only use this when we get up to around 30 volts, because what's the difference when I calculate what's the difference between 30 volts and 29.3? They're just not enough to worry about, right? You understand? But when we get down in the low scales, like 5 volts and stuff like that, there's a lot of difference between, if you check the difference, there's a lot of difference between 4.3 and 5, right? You understand that? And how much voltage we're going to get out. So this is the one we're going to use. We're going to use the practical model. We call this the second approximation. Shows the barrier potential of the diode, which forward bias acts like a switch with a small battery connected in series. When reverse bias, it acts like an open. So this is the one we're going to use right here. So what are we going to use in our formulas for silicon? About 700 millivolts, right? And for germanium, we'd use what? 300 millivolts, Rich. Now, if I was an engineer and I wanted to calculate, I needed to know the resistance of the diode. I needed to know what it dropped at different current levels. Then what we would use third approximation. So most of your engineers are using this. Shows that in the forward diode, the forward bias acts like a switch with a very small resistor, and that's the way it acts like. So what that means is, as the current flow goes up through the diode, the voltage drop the forward voltage drop actually goes up, but it's not going to be much. I think for ours, these are 1 amp. These are 1 amp diodes. And so the little black ones that we'll be using, these are 1 amp. And it says they drop around, I forgot, 500 millivolts at the barrier and around 1.1 volt with 1 amp floating through it. But 1.1 volt and 700 millivolts is just basically not much to worry about, right? You understand that? What about 400 millivolts difference? So this is the actual curve. So it actually starts conducting, then we have a need that occurs around 7/10 of a volt. And then when it starts conducting, it's not straight up, it's a what? It's a slope. So the voltage actually increases a little bit when current goes up, and it drops down when current goes down. But for practical purposes, 700 millivolts works out real well, because what we're doing back in DC, what did you have to do to all your resistors? You measured them, and then when you did your calculations, you didn't use the color coded value, you used the measured value, because you were trying to prove Ohm's law. You're just trying to prove that what V is equal to I times R. You're just trying to prove that all Ohm's law formula. After DC, guys, we don't use measured values anymore. We use color-coded values, which means all our math is going to be close, but it's not going to be exactly right, right? Y'all understand that? Because we understand now why our math is going to be perfect, but everything we're going to use is going to have a tolerance. Your diodes have a tolerance. Your transistors have a tolerance. And if you try to fool around with those tolerances, then it's going to be, an engineer might want to do that, but we don't need it. All we know is if I calculate 5.4 volts and I get 5 volts, I say that's great, right? You understand? So that's why you did that. And your lab book is going to tell you to measure the resistors. What are you going to do? You're going to mark that out, because we're going to use the color-coded values. It's just that we're going to understand that our measured values and our calculated values are not going to be the same, but they're going to be really close. Sometimes they might be, really close. So that's why we're going to use 7/10 of a volt. We're not going to use this. We're not going to use these slopes. Well, we're going to consider that there's no current flow when it's reverse bias, because we're going to be in the nanoamps, right? You understand? And we're going to act like it's a closed switch when it's forward bias, but after the 7/10 of a volt, because we're not going to be dealing with high voltage here for obvious reasons. So I think the biggest thing we deal with is 12.6 volts of RMS. We're going to assume there is, but there is. It's so small, but it's limited by current. By the way, the reverse bias leakage current is directly proportional to the temperature. So we can use semiconductors to measure temperature, and we have a device called a thermistor, and that's what it does. It's just semiconductor material. Because what happens when semiconductor material, it varies its resistance with what? With temperature. So we know a multimeter is an easy way to check a diode. A good diode will show reverse bias. If we're doing with a meter that does not have a diode scale or a p-n junction scale, what we're looking for is an extremely high ratio between forward bias and reverse bias. And luckily, our digital meters, remember, when you turn your meter on resistance, it becomes a source, right? You understand that? And it's trying to push current through the load, and then it calculates the resistance from the current. So what we're doing is, when I've got it on ohms, what happens is we're using what we call a constant current source, which means what your meter does is it raises the voltage into a certain current flows through the circuit. And it's usually around about 10 milliamps. It's not much at all. We can measure this. We can put a meter on ohms, and then we can come up and take another meter, put an ammeter, and measure it. Okay. So what they do now is it calculates this voltage right here, and it's milliamps. So the milliamps and the volts are going to be together, right? You understand what I'm saying? Yes or no? So if I was used, if in 1K, if it had 1K ohms, how many volts would 1K ohms? How many volts would it cause 10 milliamps to flow? V is equal to I times R, 10 milliamps times 1K. So it's not 10 milliamps. It can't be. Must be 1 milliamp. So 1 milliamps times 1K, what would that be? It would be 1 volt but instead of my meter measuring 1 volt, it would display 1 k ohm. And that's the way the meter works. That makes sense? So 1 milliamp, I could come out here and put anything. So I could say, 1 milliamp and 2.2 K. Well, it's going to drop 2.2 volts. And so that's the way your ohm meter actually works. So it's actually putting out a constant current, and then it's measuring what voltage is required to cause that current to flow, which is pretty neat. So what we can do is we can use an ohm meter, and what we're looking for is a large forward to reverse resistance reading between forward and reverse bias. Are we okay? Are you something wrong? Go ahead. Well, guys, this is college. I don't know what else to tell you. So I had to go through it too. So if you have questions, you need to ask them. So I think on my meter, it measured overload when it was reverse bias, and it measured 1.2 meg ohm when it was forward bias. Now, how do we forward bias it? So we got an ohm meter. It's got 2 leads. One of them's red and one of them's black. So we got a red lead and we got a black lead. Which one do you think is the positive lead and which one do you think is the negative lead? Okay. So what we would do to forward bias this thing is we would do what? We would take the red lead and put it on the what? The red lead, and we'd put it on the anode. And we'd take the minus lead and put it on the cathode. And then we would record the reading, and then what would we do? We'd swap them around, right? Understand? If we was measuring resistance. But most of our digital meters now, what do they have? They have a watt scale on it. Yeah, they have a p-n junction scale. So what we should see here, if I forward bias, if it's silicone, it's going to measure around what? Approximately 700 millivolts. Because what it's doing now, instead of interpreting it as ohms, it's going to tell you what voltage was required to cause it to start conducting, right? You understand? So we still call it an ohm meter, even though it's displaying what? Volts. And when we reverse bias it, most meters would show an overload. This yellow meter that I've got shows what it shows if you hold it up in the air, like 3.1 something. So it's a little. So your meter should measure overload for reverse bias, and it should measure around 0.7 of a volt if it's silicon, and it should measure around what? Right, and for germanium about what? 300. And we check it with, and this is any device that's got a p-n junction we can do this with. So we can check bipolar transistors. We can check junction FETs. We can check SCRs if we do a little silicon control rectifiers if we make a little modification to our test. So there's a lot of devices that we can check with this p-n junction. So anything that's got a p-n junction in it, we can check it with an ohm meter. Even though it's reading volts, we still say that, so unfortunately. So most DM multimeters have a special scale for reading a silicon or germanium p-n junction. Huh? Yeah, it's a digital, but I'm sorry. Yeah, I know, you're right. When you get into computers, we use hundreds of acronyms. And so there's websites that shows you all the acronyms that we use in computers. So I went to that thing a lot. So when this scale is selected, the digital multimeter will display the approximate barrier voltage of the diode when forward biased, and that's when we need to put the red lead on the anode and the black lead on the cathode. When reverse bias, the digital multimeter would display the same voltage that it displays when the meter leads are held open. And why I put that, because if I get that yellow meter out, that Sperry, and I hold them up, it shows three something, 3 point something, and that's what it'll show on that meter. Most of your newer meters will show overload when you have it reverse bias, and then they'll show the junction when you have it forward bias. So this meter is kind of like my Sperry. So it's showing 700 millivolts forward bias, and it's showing whatever the meter shows when you hold the leads watt up in the air. Like I said, most of your new meters are going to show what for reverse bias. They're going to show overload. So it would be very surprising if any of y'all didn't have a meter that showed anything else but overload. But it's whatever you show, whatever it shows when you're just holding your meter leads up in the air, not connected to anything, right? That's what it'll show when you when you reverse bias. So on these, how do we identify the cathode? It's got a stripe around one end that's going to identify the cathode, and the unstriped end is going to identify the anode. And here, so what's wrong with this guy on the diode scale? Would it be good or would it be bad? Well, the first one is reverse bias because if the forward bias, you're right, the meter's forward biasing it, but it's showing 2.6 volts. And then when they reverse bias, it's showing 0 volts. So is it good or bad? Bad, yeah. Good. Everybody okay? You understand? Yes or no? Okay. We okay? Yeah, it's supposed to be about, well, it's not supposed to be 2.6 volts. It might not be 0.7 because it might be your germanium diode, but it's still not going to show 2.6 volts when it's forward biased, right? You understand that? This is one of the rectifiers we're going to get in. This is going to, I'll show you how you can read this. So what do we make up? So a power supply, did I tell you, we went over the block diagram. What's the basic makeup of a power supply? Normally the first thing we have is a what? What's that the symbol for? Y'all haven't seen this symbol before? Yeah, but it's got two on both sides, and then it's got this in the center. Y'all hadn't seen that formula? I thought we showed you that. This is a transformer. What's the symbol for a generator? It's just a circle, right? This is an AC, right? This would be the second thing. And this would be our rectifiers. And right now we're looking at halfway. This would be a full wave, guys. And then we have what's next? Close. What's this guy right here? We did look at that last class. Filter, right? Yeah. Could be a capacitor, could be an inductor. We're going to use capacitors. And one advantage capacitors have over inductors, they're just so much cheaper. And switching power supplies or switch mode power supplies, they use inductors, but we'll look at those power supplies. And then the last they have on this, they have a regulator. And what does the regulator do? We talked about that a little bit last class. Now this is our check valves right here. So your car's got a voltage regulator. Everybody understands that. So what does that do? What does the voltage regulator on your car do? We'd be in trouble if we didn't have that on a car. Because how much EMF we get, how much voltage we get out of a generator is determined by one thing, it's the speed of the motion. Does your car run at a constant speed? Does your engine run at a constant speed all the time? So what would happen, in power varies with the square of the voltage. So what that means is you're sitting there idle and nothing would work. Your radio wouldn't work, nothing would work. When you got up to speed, everything would burn up, right? So we got to have a regulator. So what's the regulator do? And it's maintaining a constant output, right? You understand that? It makes your alternator put out a constant output. So that's the true on these power supplies. Well, when I showed y'all last class, is that when I put another resistor across that thing, the ripple voltage went up, right? You understand, which you mean cause the output voltage go down. So it means if I didn't have a regulator inside these trainers, every time you hooked a load, so you'd come up there, you'd measure the voltage before you hooked the circuit up, and as soon as you hooked the circuit up, the voltage wouldn't be the same anymore, it'd be lower. Because if there's not a regulator to maintain a constant output or try to maintain a constant output, that means the voltage would vary with load. So that's what the regulators do. They're going to try to maintain a constant output with what? With load. And what did I use that most people have on their cars that uses regulation? A speed control, right? You understand? So as long as you're on a nice flat road, that sucker regulates almost perfect. You can put it on 80 miles an hour and it'd be right there. But if you start up a steep hill, it might start doing what? It might start going down. And if you go down a steep hill, it might go above it because you're gone out of the limits of what the regulator can do. So regulators can only maintain so much. So if you go out there and get a 2-gauge wire and put it across your regulator, it's going to drop to zero. Your battery will probably blow up. Don't do that. Because you've exceeded the range of that, right? You understand that? I had a car, it was a Vega GT, and a Vega GT, they don't make them anymore. Vega, Chevy Vega. I love that little car. So, but it had a hatchback on it, and we had hauled a trailer, and I'd hooked it up to my tail lights, and I had a dog chain back there. We had a dog. I used to have a Alaskan Malamute, a beautiful dog, and it shorted out across that carpet, and my lights went dim. So when my lights went dim, that means I was exceeding what my alternator or my regulator could do, right? It caught the carpet on fire. And I pulled over on the side of the road, and I jumped out and started running off and said, "Rich, that's the only car you got." So I went running back and opened up the hatchback and threw the carpet out, and I was okay. But I exceeded, yeah. Well, I did have insurance, but I was where I was at, So, but I exceeded the range of the regulator, right? So I said, "What's going on?" So this is a printed circuit board, guys, and we'll look at this. And like I say, you can see how these things are laid in there, and we'll show y'all how to check these things. A lot of times when we buy these guys, what they're going to do is they're going to integrate them inside a package. So this guy right here is the same thing. It's four diodes in here. So we'll show you how to check these. These are what you're going to run in most often. Instead of having these 4 diodes, you're going to have one of these in there. And when we open up the trainer, it's going to have this same arrangement, but it's not going to have diodes. It's going to have one of these in there. And you can look at it, and it's got 2 leads labeled AC, and then it's got 2 leads labeled plus and minus. We did have one that burned up, and I replaced it with 4 diodes. I don't know if we got it here somewhere. So this is basically just talking about how to test the diode, right? Everybody okay? We're going to test the diode with our meter on the watt. Yeah, but what our meter? How are we going to set our meter? PN junction. I got their meter. I think all I've got is, well, we got all these up here, guys. But the battery's dead in this one. And if you don't read anything, guys, that means your meter might not be putting out enough current. So you might need to change your ohm scale, right? So mine's on ohms. Yours is auto ranging, so yours should be okay. I prefer these meters because I prefer meters that has the scale on it because I don't have to think about what the meter's telling me. We have this happen all the time in DC. They'll put the meter will come up and say 0.3 k ohms, and they'll write 0.3 k ohms, right? You understand that, instead of writing 300 ohms because the meter don't scale right. So I like this one right here. I like these because what they do is you decide what scale you got. So now overload means something, right? You understand that? So this one, I've got it on ohms, I think. I think I got it on the 4 meg scale. And so this is what I'm going to come over here and we'll figure out what this is. So this is about 540K, right? And this is what people do. So what they'll do is they'll write down 550K, 0.55K, and that's illegal engineer notation. So meters do not range using illegal engineer notation, because what we have is we have either 2,000 count meter, which is going to range on 199. It's going to range on twos, right? You understand? No matter what they are. So if I got a 2,000 count meter, when it gets up to 199 ohms, then it's going to go to 0.2K, right? 0.20, which is actually 200 ohms. We have a 4,000 count meter. This is a 4,000 count meter. How do I know it's a 4,000 count meter? Because all my ranges are in what? Fours. And then we have 6,000 count meters, which are very, very expensive. So your cheaper ones are going to be 2,000 count meters. How do you know it? Because all your ranges are going to be twos. If it's an auto ranging meter, it's going to range on 199, right? You understand that? So this one looks like this might be the cathode if it's good. Okay. So it's measuring 450K, right? And then I come over here and swap it around. Ooh. So this guy looks what? Bad, yeah. So let's put it on long scale and see what it shows. You're exactly right. And this might be bad. Like I said, all these were donated. Oh, this way shows good. So what first thing you do, this is what my meter shows me when I see it open, right? Okay, so let's put it back on ohms. Let's put it on a smaller scale. Uh, 126, 126K. Don't touch it, Rich. There we go. I must have been touching my lead a while ago and it was measuring me. So this is reverse bias. And this is it has to be forward bias. The ratio between overload, which means my meter can't measure it in 120. So I didn't see the symbol on this, but I just found out that this is the cathode, and so the pigtail must be the anode. Okay, makes sense. And guys, when you put it on ohms and you put it up on these high scales, you need to be leery about touching both of your leads, right, with your fingers, because your meter might actually be doing what I did. It might be doing what? Measure me, right? So here, this is the cathode. I can see that one because I can see the line. Here's the anode. So this way it's measuring about 363K. And then I'm going to come over and flip it over. And now it's measuring overload. So this is pretty easy to see with an ohm meter. Y'all might want to see what it does on y'all to see what happens. So y'all can come over and get one of these. You go, Brian. Now, on that, I think it would probably be difficult to see if it's a germanium or if it's a silicon. Oh, yeah. If I had a silicon diode to compare it against, notice a while ago it was 200 and something K, right? You understand that? But when I come over measuring this in forward biased, this is only 17K. So it's a lot lower. And when I flip it around, so this guy's measuring in both directions. But one way I was measuring what? 17K. This way I'm measuring 300 and something K. So that's the big high ratio. I'm going to put this on the diode scale and measure it. So this is forward bias. So it's measuring around 300 millivolts forward bias. And then when I flip it around, it's showing me that. So what type of diode is this? Around 300 millivolts. Around 300 millivolts. 700 millivolts is what? Silicon, right? And around 300 millivolts is germanium, right? Here's this one. Of course, you can tell this is a very low current diode because of its physical size. So it's just like I said, it's just like water valves. The more current, the more forward current the thing can handle, the bigger the diode's going to have to be, right? You understand that? So this guy right here is probably rated in milliamps. And we can see, y'all can see the black lead on it, the black side right there. So that should be the cathode. This right here should be the anode. And it's measuring 727 millivolts. And then when I reverse bias it, it's measuring what my meter measures when it's open. So what type of diode is this? Is it silicon or germanium? Is it good or bad? It's good, right? You understand, because it measures right. So if it measures the same thing in both directions, it's bad, right? You understand that? If it measures 0 or anything like that, it's bad, right? You understand that? By the way, when you get into these real high current devices, they are heavily doped. So they're going to be a little, so when I forward bias this one, it's not going to measure 7/10. It's going to measure around 400. Now this is still silicone. It's just that it's got a lot more current carriers in there, right? You understand that? But I can still tell which is the anode and the cathode, and I can still tell if it's good or bad. So this guy right here is good. And that's this one right here. Well, there's the diode symbol. You just can't hardly see it. You'll have to look at it when I pass it around. So last class, I asked y'all to bring y'all